Good morning, everybody. So, today we are discussing coordinate systems, which is a very important component of GIS software that we use in order to make measurements as required for our work. So, let's begin by understanding what coordinate systems are and why they are fundamental in geospatial sciences. A coordinate system will provide a framework for defining locations on the Earth's surface. This system allows us to accurately reference spatial data and ensure that different data sets will align correctly. There are basically two types of primary coordinate systems, of which the first one is geographic coordinate system. We might have heard of this many a times. Its short form is GCS, Geographic Coordinate System. This is a three-dimensional reference system which will use latitudes and longitudes to define locations on the Earth's surface. It is based on a spheroid and includes a datum. Datum is much like a reference surface which defines the size as well as the shape of the Earth. Now, this is about geographic coordinate system. The other type of very primary type of coordinate system is projected coordinate system or PCS. Now, unlike geographic coordinate system, a projected coordinate system translates the three-dimensional surface of the Earth into a two-dimensional map. It will use units like meters or feet and is very ideal for distance and area measurements. Examples of this will include universal transverse Mercator, which will be at the center of our discussion today. Also, state plane coordinate systems. Now, we will also touch upon the concepts of datum such as WGS 84 and NED 83, which are very essential for establishing the origin and orientation of the coordinate system. In GIS applications, selecting the correct coordinate system will ensure that your spatial data layers match and that your measurements are very accurate. Misalignments, which are caused by different projections or datums, can also lead to serious errors in analysis and even while preparing your map layouts, that is, map outputs. As we proceed, we will also explore how to choose the appropriate coordinate system for different types of projections and how to reproject data in QGIS. That's a very small hands-on that we will take up in this particular class. Look at this particular diagram. This represents the basic layout of the geographic coordinate system or GCS. Uh, This is used to locate positions on the Earth's surface using a grid of latitude and longitude. So you will see grid of latitudes and longitudes here. The equator, shown as the horizontal red line, this represents 0 degrees latitude and it divides the Earth into northern and the southern hemisphere. Hemisphere because half of the sphere. Then there is also a prime meridian, which is a vertical red line, which represents 0 degrees longitude, dividing the Earth into the eastern and the western hemispheres. So latitude and longitude values are measured in degrees. Latitude ranges from plus 90 degrees, that is at the North Pole, and minus 90 degrees, which is at the South Pole. Longitudes will range from plus 180 degrees east of prime meridian, and west of prime meridian, it is minus 180 degrees. Now, as the map shows over here, the top right quadrant has positive latitude as well as positive longitude values. This includes parts of Asia and Europe. The top left has positive latitudes and negative longitudes, covering most of the North America. The bottom left quadrant has both latitude as well as longitudes which are negative, mainly South America. And towards the bottom right shows negative latitudes and positive longitudes, which includes regions like Southern Africa and parts of Australia. Understanding this layout is crucial, especially when working with geographic data, especially while interpreting coordinates or entering location points in GIS software. Even in USGS Glovis, you must have seen that if you want to enter any values, then you have to know whether a particular latitude longitude is negative or positive. Coming to next. So this is the cylindrical projection system. This diagram will introduce one of the most common types of map projections, which is called cylindrical projection. You have to imagine wrapping a cylinder around the earth, aligning it with the equator. The line where the cylinder touches the ellipsoid is called a line of tangency. You see, line of tangency, or also called center of gravity. Or even at the center meridian as well. Depends upon how the globe is getting wrapped. The image on the left shows how the cylinder intersects the Earth's ellipsoid. The central meridian is the reference longitude that the projection is centered on. Once we project the geographic features from the globe onto the surface of the cylinder, we can unroll, right? We can unroll the cylinder to create a flat map, as you see here in the right side image. This method forms the basis of projections like the Mercator projections, which is useful for navigation because it preserves angles and directions, but it distorts size definitely. Especially near the poles, the size is distorted because you will see poles are over here, and then you will see that it is projected onto the paper, because of which there is a lot of distortion. But along the meridian, you will see very less of distortion. So this is how the map looks. Antarctica is definitely not this big, or Greenland is not really this big. Now, coming to the universal transverse projection system, which forms the core of this discussion. Now, we will discuss the mechanics of this universal transverse Mercator or UTM projection system. It is based on transverse Mercator projection, which is also a variation of cylindrical projection. Let's break it down. Unlike the standard cylindrical projection, where the cylinder is wrapped around the equator, on with this transverse Mercator, it uses a cylinder that's turned sideways and aligned along a central meridian. The central meridian is tangent to the earth, meaning if it's where distortion is minimal. Along the central meridian, distortion is minimal. The cylinder will intersect the globe along the meridian, like how we saw in this particular picture. Now, when the cylinder is unrolled or developed into a flat surface, it will create a map with very high spatial accuracy. Um, High spatial accuracy, but near the central meridian. And as you go away from the central meridian, you will see that the distortion will uh, increase as you move east to west or away from it, or away from the meridian. Now, this is the foundation of the UTM system, which divides the globe into 60 longitudinal zones. So, that is what exactly you see here. Um, each of these longitudinal zones of the 60 each is using its own transverse Mercator projection to ensure accuracy. That means for each of these strips, the globe is wrapped around in a cylinder, making a cylinder of the paper multiple times, that is 60 times, such that what happens, the distortion is kept to minimal. Okay. Now, what are the key features of this? Each zone is 6 degrees wide. you will see that each zone is 6 degrees wide and is centered on its own central meridian. So all of them have a central meridian where the um, paper was wrapped around, and then it was opened and it was cut into a strip, and there are altogether 60 strips, because of which the distortion is minimized. So within each zone, locations are measured in meters, and scale distortion is very minimal, making UTM zone very ideal for engineering or topographic and also scientific applications. The map on the right side of the slide shows how the Earth is projected when using this method in this particular picture. This approach enables detailed and accurate mapping over relatively narrow strips of land. We should now consider a clear comparison between a clear comparison between two fundamental types of coordinate systems which are used in geospatial sciences, which include geographic coordinate system, as we discussed earlier, and also projected coordinate system. So we will differentiate between the two. Geographic coordinate system, if we talk about, it uses a three-dimensional spherical model of the Earth, whereas projected coordinate system uses a two-dimensional flat representation of the Earth's surface. In GCS, that is Geographic Coordinate System, coordinates are expressed in degrees, latitudes, and longitudes, whereas when it comes to projected coordinate systems, coordinates are in linear units like meters or feet. Uh, Most commonly used geographic coordinate system for global data sets, and when accuracy in shape and directions over large areas is needed, is geographic coordinate system. A commonly used one is geographic coordinate system. And based on map projections such as UTM transverse Mercator projected coordinate systems we are talking about. They, these projected coordinate systems are essentially based on map projections like that of universal transverse Mercator or Lambert conformal conic or simple Mercator. Now, geographic coordinate systems, this is where distances and areas are distorted, especially when we measure them directly from degrees. But when we consider projected coordinate system, it can be better used for distance or area and also direction calculations in a very localized zone. That means from different two strips we are not going to use. What are the examples of these GCS? Examples of geographic coordinate systems will include WGS 84 and NED 83. Read a little about them. Projected coordinate systems are always based on there must be an underlying geographic coordinate system, and then it is projected onto a paper. When you view a map, to just put it in a different way, when you view a map, when you look at a map or conduct spatial analysis in GIS, you are typically working in a projected coordinate system. So always remember, whenever you are trying to make any calculations like distance calculation or area or direction calculation, you have to use a projected coordinate system. And essentially, we are going to use universal transverse Mercator because that is the most ideal one with least distortion rather than using any other. This will ensure measurements are very accurate. However, the base location data may still be stored in geographic coordinates. When you collect some data from field, you will definitely collect them into geographic coordinate system. That is degrees, minutes, second in that particular manner. So choosing the correct system will depend upon the scale of your work, how big is your work, the region that you are working in which particular strip it falls, or where exactly it is, how close to the pole or how close to the equator, things like that. Then also a type of analysis that you are performing. So you have to always remember that a projected coordinate system cannot exist without a geographic coordinate system under it. That means under this projected coordinate system, there is always a geographic coordinate system. Um, uh, because its projected coordinate system is essentially a transformation from spherical to a flat surface. We will stop here and continue for the next session.